So in this demonstration, we're going to have a little bit more of a comprehensive look on the capabilities that are available in WATS and cover some of the typical use cases that you will find. How to use dashboards and extract data for high-level reporting. How you can easily access and drill down into frequent failure data. Understanding how retesting is affecting your company and performance, and also process capability analysis to understand how good your actual test coverage in production is. And finally, we're also going to touch a little bit on unit tracking capabilities, both from an individual point of view, but also tracking batches of units. So if we start on that high level data reporting that I mentioned, there's a lot of different dashboard components that you can configure yourself. One example is shown here, where you can see a geographical overview of the different test stations that you have with certain KPIs elements embedded in. So you can see here the volumes of test reports and the yield statistics per site or per station that you have. You can also find more granular, more detailed information in these dashboard components that you have. Like you can look at over here, you have an overview of the specific steps that has most frequently caused your units in the test to fail. Down here you have information on repair causes or repair categories as well in production. So the purpose of these dashboards is to give you a quick overview, quick insight into what is happening in your factories. And you can also drill down directly from these dashboards into the data that is underneath it. So if we start on the first of the scenarios that I specified, understanding the frequent failure causes that you have. You can use this yield report function. So that is available from the right-hand menu here. And if you go to yield report, so I have a pre-configured filter here for a data set where we have three products. It's OLC 130P and C. Those are subcomponents into the final build that is OLC 130. And you can also see the test operations that are used here are PCBA test for both of these and final function test for the final unit. This report will give me some statistics. Again, you can see the volumes of units tested under here, first pass count, and first pass yield percentage as well. If you would like to customize the columns in here, you can do so in this column option. The same data is also available graphically down here, and you can also look at this per product group. So these are all of these part numbers are combined into a virtual product group that we've configured in WATS that is called OLC power supply. So that information is also available down here. But if I want to use this data now to quickly prioritize, understand what are my bigger inefficiencies or bigger problems, you can quite easily see that the first pass yield of this OLC 130P product is 1% lower approximately than OLC 130C, but they have more or less the same volumes. So purely statistically speaking, we then have a higher failure rate in this data set. So I'm going to use that as an opportunity to actually prioritize that I want to understand what is going on in this product, OLC 130P. Now I can drill down into a lot of different reports in here. I can break it down by product revision, for example. If I go into this product and test yield, I can break this down by test station as well to see how does this specific product perform on the different test stations and what the yield on those are. But in this case, I'm going to look at this test step yield and analysis report. So what this report will tell me is the performance broken down by the different test steps that we have available. The first Pareto you can see is the step execution time. So it basically just shows me how much time are the different test steps we have taken on average, minimum execution time and the maximum execution time, to better understand what is the time component in test. Are there any specific test steps that are acting like a bottleneck in your throughput? The next example, or the next Pareto down here, is the top 10 failures for this product. So you can see on the left side, this charge rate C31 is the one that stands for most of the failures. It has failed 163 times in the first test attempt. And note that now we're only looking at the first test run here. I could be looking at all test runs, and that failure count will probably change then. So 163 times it has failed, and that represents about 30% of all the failures that you have. The next fail cause is this chroma measure current. It failed 98 times, and combined these two steps represents about 47% of all the failures. So this is a quick way for you to prioritize what failures should you prioritize, or should you attempt to fix first. Now, if I want to understand the actual reasons for these failures, I can click on the graph. And it's going to open up this step details view. So now I'm actually down looking at the data from a measurement level. There's a lot of details. I'm not going to go into the specifics of those. But the red lines you can see here, those are the test limits that you have. And they're red for each individual test report, so they're not overlaid in here. And the light blue lines here are the actual measurements results for this test step, charge rate C31. And if you look over here on the right hand side, you can see it looks to be more failures associated with this side. And that's also something that is seen up here in this pass-fail status chart. You can see most of the failures are actually over here. So to better understand what is the root cause of this, I can group this data by different meta parameters. So in this case, I'm going to group them by product revision and see what happens then. And it's quite obvious then that this revision 9, we've got two revisions, 9 and 10 here. If I toggle off revision 10, you see that is the brown field, and there are some failures to this revision 9 dataset as well, but it's far more on revision 10. So the preliminary conclusion here, this is probably something that has to do with a revision issue, something that has changed from revision 9 to revision 10. So what I can do now is to also look at the repair information for this data to see what is the what kind of diagnostics has the repair technician given this product. So for that, I'm going to open up the repair analysis report here, and I'm going to take away a lot of these different results, and I'm only going to look at the fail step report because I want to see for this specific step what the data tells me. So really you can see that the actually the charge rate C31 is also the most frequently repaired test failure. And if I now open this one up, then it's insufficient soldering that is the primary reason for this test to fail. But now I'm actually looking at both revision 9 and revision 10, and I know from the measurement view that it is revision 10 that was acting in a negative way. So I'll add revision 10 here, I'll apply this filter, and I can look again on the result for this charge rate C31. So you can see that the count went down from 50 to 17. But now all of a sudden actually the repair code, or the repair cause, is due to a component issue where the component was out of specification. That's the most frequent reason for this failure. So that's one example how you can quickly drill down into the frequent failures that you have, but also use repair information to get further validation of the root cause. Now obviously, if you would like to use this high-level drill down, as we saw now, where you go from like the yield metric down to the actual failures underneath, you need to have a representative or a good test coverage. So the next example that we'll have a look at is the process capability analysis report and how you can use that to effectively evaluate the test limits that you have. So I'll use the same set of data, OLC 130P here, and I'll select process capability analysis. I'll specify in this secondary filter what part number I'm looking to analyze, and what will present me with a list of all the different steps names in this dataset, or the test steps that you have, along with many other statistical parameters in here. So if you're not familiar with process capability analysis, or CPK index, it is basically a ratio between the test limits that you operate with and 3 standard deviations of the measurements that are underneath it. So if it's a low number that is represented as a red number here, it indicates that either your test limits are too narrow or maybe the process is too unstable. If it's a green number, then it's indicative of a relatively good fit. And if it's a blue number, a high number, typically means that the test limits are too wide compared to the underlying process, or the variations of the measurements that you have. So there are 2 relevant columns that we can look at here. One of them is the CPK. So what is this index for all the measurements? But over here you have one that is called CPK without fail. So if we filter away the test steps that we knew that are flagged as failed in your report, how does the CPK value look then? If we look, for example, on this measure isolated 12 volt step, the CPK value is relatively low, but when we take away the failing steps, it is relatively high in here. And I can drill down to look at the measurements here, same as we did before. And this is going to open the step details report. So what we can see here is that, so there are some failures to this step. It's not a lot, but they are failing off the chart. If I scroll out here, very far out of the away from the average value. If I toggle these failing measurements off, filter them away, then you can see there are many outliers in this data set that are not detected by the red limits here, or the test limits that we have. So these are things that are not flagged as failing. You can see if I hover over, you can see the step results obviously as passed here, but I can also click on this directly and it will open up the test report for this. So one thing that is clear is that the test report didn't fail either. So very often it could be that there are some other failures that will trigger the overall test to fail, but that was not the case in this example here. And I can also click on the serial number itself here to access the serial number history for this unit. And if I scroll down here, you can see in the history, this serial number here was tested as a PCBA test, and that was the result that we were looking at. Later it has been tested as a subunit in a different product, so that's the OLC-130, or the parent unit. And relatively recently it has also been tested in a RMA test where it has failed. And I can also look at the unit history or the work in progress tracking information for this specific unit to see what its current status. And you can see here that this is flagged as scrapped. So that's a quick example of why it's important that you're able to better control or better track the performance of these test limits to avoid that you have these downstream failures. A poor product is built into another product that goes maybe out to a customer even and fails there. So the next example we'll have a look at is related to retesting. And for this I'm going to look at the same data set still, OLC-130P, but I'm going to use this periodic yield. So what this report does, it breaks down the data into groups of time. So the grouping here is per month. And what I can do is I can expand this period. And all the way down now here, I'm going to be shown a chart that tells me for all the units that were passed or tested as good in this period, in what attempt did they actually pass? You can see over here there are 24 units that passed in the second attempt. You have 10 units that passed in the third attempt. 2 units that passed in the fourth attempt. I can click on this and it's going to open up the serial number history. If I just look at one of these, then you can see down here it's been tested as, it failed 3 times. It went to repair, to this module production repair. Tested again as passed in PCBA, and it's been later tested as a subunit. So that's, all is fine. No concerns there. But if I go further to the right on this chart, you can see you have one tested 18 times and one tested 19 times on this. So that's maybe something that I want to look closer into. So again, I'll open up the serial number history for this unit. I can expand on this one now, and you can see all these the test reports up here. It was tested on September 23rd, a lot of time, one time on September 24th, and the remainder of times September 25th, where it eventually passed here. And it's been tested as a subunit later for this here. It's more clear in this flat view here. So here it's been tested as a subunit on the final function test, but also relatively shortly afterwards it's been tested in an RMA test and has failed there. So if I would like to understand what's the reason for this failure, I can drill down into the step details. Those are Retest step yield analysis report that we had. There's just one observation here is you can see that this last attempt where it passed, this was done on a different test station. So all of these were done on OLC FT01, but the final test was done on OLC FT02. So I'll drill down here, test step yield analysis. I'll make some modification to the filter that I would like to see all test runs, not only the first one. And you can see, well, one observation again is that you have two different software file names, two different versions here, version 1.11 and version 1.12. I'll click on this again. I'll see the top 10 failures, and it's a different step. In the previous example, this was charge rate C31. Now it's charge rate C41 that is failing. And I can click on this again, open the step details view, and all of these measurements, you can see, they're failing above the upper limit here. But when it passed over here, actually, the high limit went up. So it went from 3.8 to 5.3 for this. And this is the test that was done on a different test station. That has a different software, a lower version of the software sequence or the test sequencer. So the example shows that, okay, you probably had a poor product that went into the final build, and the fact that it actually was tested in an RMA, that it failed in shortly afterwards, strongly indicative of the same. But you also don't have control of the test software that you're running. So that's something that can actually be where you can use the software distribution module in WATS to automate, to make sure that that scenario is unlikely to happen, because as soon as a new revision of the software is available, it's distributed automatically to all the test stations. So to look further into some of the unit tracking capabilities that we have, I'll drill further down into this unit history report over here and expand. So what this report will show me is not only the test results, but it will also show me the work in progress phases that is passed on to WATS here. So you can see here that it passed final function test. So now I'm looking at the master unit, OLC 130. The work in progress MES API in WATS was then used to give it a status as finalized, but it's then come back RMA test, it's been failed, it's been sent to repair that has taken place, and afterwards this unit has been scrapped. And WATS can also show you the aggregated visual information on these work in progress phases. So the WIP tracking, work in progress tracking here, will show you a graph of where in this production flow are your products currently at. Okay, so that concludes the most common use cases for WATS and how you use this high-level data to drill down and see the more detailed data that you have underneath, how you can use this tool to better prioritize and better understand what is actually happening in the factory.